Ever wonder how you actually fit heavy zero-knowledge cryptography onto a lightning-fast blockchain without everything just grinding to a halt? Well, in this explainer, we're unpacking the Aurora framework to see exactly how it bypasses those major performance bottlenecks. So let's just get right into the central tension here. You've got these mathematically intense ZK proofs, right? And you're trying to cram them into a network that has incredibly strict computational limits. It's a classic engineering tug of war. We absolutely want that privacy, but we also need lightning-fast performance. How do we get both? Here's the roadmap for how Aurora pulls this off. We'll start with the blockchain bottleneck, move through the 3 layers, edge generation, the Rust gateway, and the on-chain notary. Then we'll look at hardening the defenses and wrap up with elite production readiness. Let's get into it. Part 1, the blockchain bottleneck. This brings us to the real villain of our story, what we like to call the fuel tank problem. You probably know that every transaction on Solana has a strict compute unit, or CU limit. If you try to run heavy cryptographic verification natively, like directly on the blockchain itself, it's just too computationally expensive. You'll literally exhaust those compute limits almost instantly. And the result? Network congestion, failed transactions, and a whole lot of wasted gas fees. You simply cannot run a high-volume ZK application this way. So, to bypass that physical constraint, Aurora uses a really clever 3-layered pipeline. Instead of forcing the blockchain to do all the math, Aurora completely offloads the heavy lifting to edge environments and off-chain gateways. Think of the blockchain not as a general-purpose computer for complex proofs anymore, but simply as a secure, immutable registry for the results of those proofs. Moving right along to Part 2, Layer 1, Edge Generation. Let's track the journey of a single private proof, starting right here at the edge. The client-side SDK is essentially acting like a private workshop. By leveraging WebAssembly, or WASM, this layer is generating those heavy ZK proofs at near-native speeds right inside your browser or node environment. And this is huge for 2 reasons. First, the blockchain is totally spared that massive computational overhead. Second, absolute privacy. Your sensitive secrets never actually leave your device. You're just transmitting a mathematical proof that your secrets are valid. That is privacy by design. Which brings us to Part 3, Layer 2, the Rust gateway. Okay, so once your proof is crafted locally, it heads to its first guardian before ever hitting the blockchain network. This is the off-chain verification daemon, and you can think of it as a really high-speed filter. Because it's built entirely in Rust, you're getting maximum performance and crucial memory safety. It handles massive parallel submissions and rapidly rejects any malformed or fraudulent proofs. By filtering out all that mathematical noise at the gateway, it protects the Solana runtime from denial-of-service-style compute exhaustion. Basically, it makes sure that only perfectly clean, valid data is ever going to cost you gas. Next up, Part 4, Layer 3, the on-chain notary. Finally, our mathematically sound, pre-cleaned proof arrives at the Solana blockchain. But here is the brilliant twist. The Solana program, which is built using the Anchor framework, doesn't actually run the heavy ZK logic. Remember, we already did that off-chain. Instead, it's just acting as a digital notary. It does a super lightweight final check to make sure the proof actually came from our trusted daemon, and then it just records a compact, immutable attestation right on the ledger. It keeps the on-chain operations incredibly lean and perfectly within runtime constraints. Now, you might be wondering, what happens if a bad actor tries to submit that exact same valid proof a second time to get duplicate benefits? To keep the state totally secure, this registry uses a 4-step process with one-time use identifiers called nullifiers. When a proof is submitted, its unique nullifier is persisted right on the ledger. If anyone tries a replay attack, the system spots the duplicate nullifier and gracefully rejects it. State integrity stays ironclad. All right, Part 5, hardening the defenses. So we've got the architecture down, but how does Aurora actually prove this whole setup is mathematically impenetrable? To get that, we need to look at the difference between standard code coverage and logic coverage. Normal code coverage just checks if specific lines of code execute under normal conditions. It's a basic sanity check, right? But with cryptography, your state space is basically infinite. So Aurora uses property-based testing to achieve true logic coverage. Rather than using predictable test data, it literally hammers the codebase with thousands of dynamically generated random inputs to make sure the universal mathematical invariants, the actual laws of this digital environments, are never broken, no matter how weird the input gets. In fact, Aurora aims for a highly adversarial 95% logic coverage. This empirically proves that the finite field constraints of this ZK environment are strictly upheld, even under extreme stress. We're talking about stopping devastating vulnerabilities like integer overflows or underflows dead in their tracks before they could ever trigger a systemic crash. And this diagnostic matrix shows exactly how they do it. It's a multi-layered defense system. You've got frameworks like ProbeTest and FastCheck doing the heavy lifting for property-based testing to find those needle-in-a-haystack logic flaws. Then, you've got native edge case tests specifically built to catch unhandled crashes at numeric limits. And finally, custom threat simulations that are specially designed to thwart proof injection and validate that replay protection we just talked about.
Finally, Part 6, Elite Production Readiness.
Let's take a look at how this highly complex architecture actually gets packaged up for developers. In the past, developers had to deal with a lot of friction, crazy multi-terminal setups, and environmental drift from juggling different toolchains. Aurora fixes this by unifying the whole workflow. They turn that messy setup into a single, simple command, make all, managed through a root makefile. It automates dependencies, builds the stack, runs all the testing matrices, and strictly enforces toolchain versions. It's a total game changer that removes setup friction entirely. Plus, Aurora's CI/CD pipeline takes a security-first approach. They use a tool called CodeQL, which actually treats the entire project source code like an interrogable database. So on every single code push, it's automatically scanning across both the Rust and TypeScript layers. It's hunting for structural vulnerabilities, injection flaws, memory safety issues, you name it. It automatically blocks any security regressions from ever being merged into production. When you combine all these elite power-ups, the jump to 95% logic coverage, the massive upgrade in developer ergonomics, and those automated security checks, the result is an optimized system readiness score of 92 out of 100, a huge jump from the baseline. What this really means is that Aurora is no longer just some hackathon prototype. By offloading all that heavy math to WASM at the edge and using a high-speed Rust gateway in the middle, it has evolved into a rigorously tested, deployable framework. It actually resolves that classic trade-off between absolute cryptographic privacy and high-speed blockchain execution. The mathematical laws are enforced, the pipeline is fully automated, the infrastructure is empirically sound. Knowing that you can now securely deploy complex zero-knowledge cryptography on Solana without exhausting the network's compute limits, the real question is, what privacy-preserving application are you going to build next? Thanks for tuning into this explainer. Keep building, and I'll catch you next time.